Hello, everyone. Welcome back. I hope you're all doing great. And finally, we are starting Chapter 2 of Physics 2 Electric Field. In Chapter 1, we studied electric charge, Coulomb's law, and many important exam type problems. Now, in this chapter, we move to one of the most important and fundamental concepts in electromagnetism, the electric field. We will learn what an electric field really means, how charges create electric fields around them, and how to calculate and analyze these fields in different situations. In this chapter, we will study electric fields due to point charges, electric field lines, electric dipoles, and also continuous charge distributions such as rods, rings, and disks. As always, this course is focused on fast, clear, and exam-oriented explanations for engineering students. So if these videos help you, don't forget to subscribe, like the video, and support the channel. Now let's begin Chapter 2, Electric Field. Now let's continue with the electric field concept. The electric field at a point is defined as the electric force per unit positive test charge placed at that point. Mathematically, we write E equals F divided by Q naught. Here, Q naught is called the test charge. A test charge is simply a very small positive charge used to detect the electric field at a point. And remember, the direction of the electric field is always the direction of the force acting on a positive test charge. The SI unit of electric field is Newton per Coulomb, or Newton over Coulomb. Also remember that the electric field is a vector quantity, so it has both magnitude and direction. Now, let's talk about the direction of the electric field. To determine the direction, we imagine placing a positive test charge near the source charge. For a positive charge, the positive test charge is repelled, so the electric field points away from the charge. For a negative charge, the positive test charge is attracted, so the electric field points toward the charge. This direction rule is extremely important in electric field problems and vector analysis. Now, let's study the electric field created by a point charge. If a point charge Q creates an electric field at distance r, we use this equation. The electric field magnitude equals K times the magnitude of Q divided by r squared. And remember that the Coulomb constant K equals 9 times 10 to the power 9 Newton meters squared per Coulomb squared. Also, notice that the electric field becomes weaker as the distance increases. Now let's continue with examples and applications of electric fields. Now let's solve our first electric field example step by step. In this problem, we want to find the magnitude and direction of the net electric field at point P. We are given that charges Q1 and Q2 are both positive E, and Q3 is positive 2E. Also, the distance A is 6 micrometers. Before starting the solution, remember an important idea from the previous slide. To determine the electric field created by each charge at point P, we imagine placing a small positive test charge at point P, and the direction of the electric field is always the same as the direction of the force acting on that positive test charge. Now let's begin with symmetry. Because Q1 and Q2 have equal charges, and point P is located symmetrically between them, the electric fields produced by these two charges at point P have equal magnitudes. Their directions are opposite to each other, so they cancel completely. That means E1 plus E2 equals 0. So the net electric field at point P is only due to particle 3. Next, we determine the distance between particle 3 and point P. From the geometry of the figure, this distance is A divided by square root of 2. Now we apply the electric field equation for a point charge. The electric field magnitude equals K times the charge divided by R squared. Substituting the values, we get E net equals K times 2E divided by the quantity A over square root 2 squared. After simplification, the result becomes E net equals 4KE divided by A squared. Now in the next step, we will calculate the numerical value and determine the direction of the electric field. Now let's calculate the numerical value of the net electric field. We previously obtained E net equals 4KE divided by A squared. Now we substitute the known values. The Coulomb constant K equals 9 times 10 to the power 9. The elementary charge E equals 1.6 times 10 to the power minus 19 coulombs. And the distance A equals 6 micrometers, or 6 times 10 to the power minus 6 meters. Substituting everything into the equation gives the final result E net equals 1.60 times 10 to the power 2 Newton per Coulomb. Now let's determine the direction of the electric field. Remember that the electric fields from particles 1 and 2 cancel each other because of symmetry. So only the electric field due to particle 3 remains. Since particle 3 is positive, the electric field points away from it. Therefore, the net electric field at point P is directed upward and to the right, along the diagonal line from particle 3 toward point P. And this completes our first electric field example. Now let's move to the next important exam type problem. Now let's solve another important exam type problem. In this example, we want to find the point on the x-axis where the net electric field is 0. Before solving, let's remember a very useful rule that applies to almost every zero electric field problem. For like charges, the zero field point is located between the two charges, and it is always closer to the smaller charge. For unlike charges, the zero field point is located outside the two charges, and again, it is closer to the smaller charge. In this problem, the charges have opposite signs, so they are unlike charges. Therefore, we assume the zero field point is to the left of Q1, which has the smaller magnitude. Let the distance from Q1 to the unknown point be x. Then the distance from Q2 is simply L plus x. Since the net electric field is 0, the magnitudes of the two electric fields must be equal. Using the electric field equation, we write E1 equals E2. After substituting the charge magnitudes and distances, the Coulomb constant appears on both sides, so we cancel it immediately. Next, we take the square root of both sides. This gives 1 over x equals 2 over 60 plus x. Finally, solving the equation gives x equals 60 centimeters. Therefore, the zero electric field is located 60 centimeters to the left of Q1, the smaller charge. This simple rule about the location of the zero field point can save a lot of time in exam questions.